Hello, everyone. I'm Zhao Li. I'm a graduate student at Dartmouth, and my advisor is Mary Hudson. I'm going to talk about the case study on March 2013. So in this study, I use a radio diffusion model to analyze this whole mass. So I can save some time on this plot. The top two panels shows the phase space density as a function of time and local radio position. It's shown for two different m values, and these two panels shows the line plots cut through different radio locations. And Sullivan drivers is plotted at the bottom panel. Beginning on March the 1st, there's a high Sullivan high-speed stream cause the PSD enhancement starting from high L star, and it gradually diffuse inward. And starting on March the 17th, there's a strong CME shock cause the dropout first. We studied this dropout use MHD test particle simulation. I'll show it later. And starting on March the 18th, it shown the PSD recovered to its pre-storm values. So the question is whether this recovery is caused by inward radio diffusion or local acceleration. We studied this by comparing our radio diffusion model with the mega experiment. And we studied whether this process is different or the same for electrons with different energies. And later this month, there are two further enhancements on PSD happen on March the 21st and March the 28th. This plot shows our radio diffusion calculation. The top panel is the phase space density for 1,000 MeV per Gauss energy, per Gauss electrons. The axis is time. The y-axis is is radio location. We use a standard radio diffusion model with the loss term represented by minus f over tau. Tau is the lifetime of electrons. And we use the Bradgam and Albert diffusion coefficient and Spritz's 2007 electron loss time. It's different for outside plasma pulse and inside the plasma pulse. It's 6 over Kp for outside and fixed at 5 days for inside the plasma pulse. And the plasma pulse location is estimated by EFW measurement. It's plotted as the black line here. And the outer boundary, we take the mega measurement from L star larger than 5 and smaller than 6 as our input to this model. So in this plot, you can see that our model reproduced the enhancement on March the 1st, on March the 18th, and March the 21st, and March the 28th. And we did an error analysis. This panel plot the log 10 of the model minus log 10 of the data. When it's blue, it means the model underestimated the PSD, and when it's red, it means the model overestimated PSD, and when it's green, it means the model does a good job. In the first half of the month, you can see there's some red here. That means our model overestimated PSD inside the plasmasphere, and we believe it's caused by our inaccurate loss models. Because our loss model inside the plasma pulse is fixed at 5 days. And starting on March the 17th, our model starts to underestimate PSD, so it indicates that there's another acceleration mechanism in addition to inward radio diffusion happened during this time. So our question here is that whether this process is dependent on energy. This slide shows a previous study by Bertgam and Albert. They ran the radio diffusion model and compare it with the crash measurement. The top panel shows for the m equals 300 MeV per Gauss, it's a relatively low m value. The solid lines are measurements, and the dashed lines are the simulation. So you can see that for this low m value electrons, there's a good agreement between the model and the simulation, and the PSD is monotonically increased with L. So it means so the good agreement means that the dynamics throughout the outer radiation belt can be explained by radio diffusion valve. And the bottom panel shows mu is about 800 MeV per Gauss, and that's about 0.6 MeV at GL. And the simulation shows a PSD increase with L, but the measurement shows a negative gradient with a maximum inside L equals 4.5, and this indicates that there's another local acceleration mechanism happened at around L equals 4 for high energy electrons. We expand this study use the recent wireless probes data. So the phase space density for 3 different m values, 200, 400, and 1000, is plotted on the left from March the 16th to March the 19th. And look at the outbound orbit on March the 18th, and you can see there's clearly a peak for large m values, not so clear for 400 MeV per Gauss, and there's no peak for 200 MeV per Gauss. And the line plot of this outbound orbit is shown on the right. So for low m values, this PSD is increased with L star, and there's no peak, and the peak starts showing at 400 MeV per Gauss, and it grows for high m values and peaked at around 4.1. Okay. And this shows, we did our radio diffusion calculation for 2 different m values. This is 200, and this is 1000. And for the 1000 MeV per Gauss, you can see there's an estimation on the 18th and on the 21st, but it's not shown here. It means that radio diffusion works well for low m values, but it's not sufficient for high m values. And this shows the MHD test particle simulation for the study for the dropout on the March the 17th. With the CME shock happened on the 6 UT, the magnetopulse moves inward from 11 RE to about 8 RE, and you can see dropout happened first on high energy particles and later on low energy particles. This is 2.5 MeV, and this is 5.5 MeV. And these 2 panels shows the pitch angle distribution, and you can see that because of the drift cell splitting, the 90-degree pitch angle electrons are lost. There's another peak in dynamic pressure after 730 UT, and it turns the loss into the loss count start from 8 UT, and it's associated with high azimuthal electric field. And Mary will talk this in details in the next talk. So these are my conclusions. The diffusion model captures inward radio transport, and it produced enhancement on the 1st, on the 21st, and on the 28th. And we tested the conclusion of Bratgam and Albert, and it shows a peak in PSD appears for m larger than 400 MeV per Gauss electrons. And we did the MHD test particle simulation, shows the flux dropout as the magnetopause moves inward. Yes.
Questions? Yes. Pat?
Very nice. I saw in your power spectral density plot where you showed the increase of that one right there.
This
Yes,
one?
that one. It looked like the, yeah, let's scoot over to the right-hand side. It looked like the power spectral density at like 5.3 actually went down. So were some of those inner electrons also accelerated up into up and out, or where did that decline go?
Where?
At 5 point, yeah, right there.
Here?
Yeah, it was higher before the event at about 5.3 and then decreased. Did that get accelerated up into the peak, or did it get lost, or what happened to those particles?
No, so these 3 lines are plotted for different m values at the same time. So to plot it on the same scale and normalize the PSD at by the PSD at the for L star equals 4.8 for each m values. So these plots are not shown in time.
The different M's.
These are different m
energies.
values.
Other questions? Have time for one? Richard?
Yeah, the empirical lifetime model you're using from Spritz is probably not very accurate. So
Yeah.
I think we can probably give you much better lifetimes based on the wave observations, both inside and outside the plasmasphere.
And energy dependent.
It will be very helpful
Yeah,
if you
sure.
can provide that. Thank you.
Okay, thank you very much again.